Hi, welcome back to AP Physics C, Unit 3, Work, Energy, and Power. I know the slide says potential energy and conservative forces, but this is actually our conservation of energy video. I actually duplicated the slides, and I guess I forgot to change the header of this video. So this is conservation of energy, not potential energy and conservative forces. Okay, that was the last video. So when we talk about in physics, what is a conserved quantity? So a conserved quantity for a system stays constant, and it changes by a definite amount that is transferred to other systems and or converted into other forms of that quantity. Basically, what we say is that it can be transformed, but not strictly or created or destroyed. Now, in this unit, we're going to look at the conservation of mechanical energy, right? So the mechanical energy of particles stays constant unless forces outside the system or non-conservative forces do work on it, in which case the change in mechanical energy is equal to the work done by the non-conservative forces. This is what we know as conservation of energy, right? And so in physics 1, oftentimes we just said delta E equals 0 or K plus U, right? The befores equal to K plus U after. Now what we're saying here in physics C is that, yes, it's going to be equal to, excuse me, not K. All right, it's going to be equal to delta E, but we're not saying it's going to be equal to 0. We're going to say it's equal to the work done by non-conservative forces. Or you can write that as delta E minus work done by non-conservative forces will be equal to 0. But another way to write delta E, right, is delta K plus U. Okay, and remember delta is final minus initial, so that should be like K final plus U final minus K initial plus U initial, right? So those are all different ways to write delta E, right? Now we're going to go through two example problems. One is going to be focusing on a pendulum because that's a lot of Unit 6 stuff, and then we'll look at dissipative forces. Okay. So here is our example problem with the pendulum. It says a particle of mass m is hung from a ceiling by a massless string as shown in figure 8.7, which is actually the one there. The particle is released from rest when the angle between the string and the downward vertical direction is 30 degrees. What is the speed when it reaches its lowest arc? So in physics 1, I'm sure a teacher probably had you look at or figure out a way to derive that height when given an angle, right? And so this is how you find the height that you pulled it back or pulled it up, right? This h here. And that comes from the triangles, okay? Or the triangle. You can find the height now by substituting numbers, or you can wait to plug it into the equation. So this is just a basic conservation of energy equation where we would say delta E equals 0, or E before equals E after. I don't know where I wrote after and then didn't write before. So it'd be K before plus U before equals K after plus U after. And then we can do some canceling now. We know that when we pull it back, we're not moving, so that's 0. The lowest point is where we say H is equal to 0. And so that just gives us U before equals K after. And U is MGH. So we call it before if you want, right? And then you have 1/2 MV final squared. Okay. A lot of times you can just see it just gives you this general M because the masses don't necessarily matter. And so you end up with GHB equals 1/2 V squared. If you solve that for V, you end up with the square root of 2GH. If you figured out what your H was here, you can just plug it in there. Or if you didn't, you would say square root of 2G L minus L cosine theta. And that L is the length of the pendulum. And so let's substitute in our numbers. V equals the square root of 2 times 9.8 times 1 minus 1 cosine 30. And it's going to give me a speed at the bottom of 1.62 meters per second. So if you did find out what H was before, This is 0.134 meters when you do 1 minus 1 cosine 30, or 1 minus cosine of 30. All right, so now let's take a look at an example that uses dissipative forces, right, or a non-conservative force. So you have a helicopter hovering 1 kilometer above. So one thing to note, our H is not 1 kilometer, our H will be 1,000 meters. The panel is going to break from the underside, plummets to the ground. The mass of the panel is 15 kilograms. All right. It hits the ground at the speed of 45 meters per second. So down here, 45 meters per second. How much mechanical energy was dissipated by air resistance during the panel's descent? All right. And so what we're going to do is, instead of it setting it equal to 0, we're going to set it equal to the work done by non-conservative forces, which is actually the dissipative energy, right? And so this is what we can call also E dissipative, okay? So E dissipative is going to be equal to K final plus U final minus K initial plus U initial, or sorry, minus U initial, not plus, because remember that's a delta. So again, we can cancel some things out. We know at the bottom we're at 0, top it's just dropping. So our dissipative energy is going to be equal to K final minus U initial. So note, you did need that mass here because we're not looking for a final speed where it would ultimately cancel out. It is dependent on mass because our energies are dependent on mass, right? So they both have mass in them. So I can now just simply say 1/2 times 15 times 45 squared minus 15 times 9.8 times 1,000. And you're going to see that this number does end up being negative because it's dissipative energy, right? This is energy lost by the system due to air resistance. So it's going to be negative 1.32 times 10 to the 5th joules. So that's how energy was lost due to air resistance in this panel falling 1,000 meters. All right, so that's it. That's unit 3 here in AP Physics C. Look forward to jumping into unit 4 soon.